them into the webinar at any time. If we run out of time during the Q&A, all remaining questions will be answered in the post-webinar email on Friday, October 30th, and include a link to the recording. So I'll now pass the webinar along to Dr. Milona.
My name is Sofia Milona, and today's presentation is on measurements of engine oils, and I will start showing you some thermoconductivity theory, the methods for the liquids, the advantages of the transient hot wire. Then I will continue about the transient hot wire theory and how the THWL1 is working. I will present you the THW software, and then I will finish with some measurements of the engine oil 5W30 and some thermophysical properties of water and ethylene glycol. Then we will move showing some models of the THW and some testing cells, and at the end of the presentation you are welcome to ask your questions. There are different types of engine oil. Some of them are the synthetic blend, high milers, and conventional. And these oils are also separated in different grades according to the temperature operation range and their viscosity. Another very important property of the oils is the thermoconductivity, and that's why we would like to present you some ways how to measure accurate the thermoconductivity of them. The primary technique of the thermoconductivity is the transient hot wire, and this is because there is a full theory behind that for the fluids, and the fluid is in direct contact with the wire all the time, which means that there is no heat loss. And because of the short measuring time, we know that we don't know convection is present on the measurements. This method, even though it's also it could be good for solids, it's not very popular, but it's a technique very easy to use. Secondary techniques like the transient line source and the transient plane source are also used for the thermoconductivity measurements of liquids, but in the case of the transient line source, the needle is very thick, which means doesn't follow the theory of the transient methods. And also the measuring time is very long. It's almost, it's over a minute, which means that for sure, especially in low viscosity fluids, the convection is present during the measurements. But on the other hand, it's suitable for solid measurements. Another method, the transient plane source, is suitable for solids, but also it's a complicated method, so an experienced user needed. And also for the measurements of liquids, the user needs to know the volumetric heat capacity in order to get accurate results. So which are the advantages of the transient hot wire? It's an accurate technique, it's very convenient, it's very fast, only 1 second, which means that there is no convection present, but even if it's present, the user can detect it directly. It's an absolute technique, and in case of the 2-wire sensor, there is no need for calibration. But in the case of the single wire sensor, as it's our THW, there is a need of only 1 point calibration. The wire is heating using a constant current source, and the temperature rise of the fluid is monitoring by the change of the electrical resistance of the wire. And from the temperature rise as a function of time, we can calculate the thermoconductivity. And from the slope of the straight line, we can predict and calculate if the thermoconductivity of the fluid is high and low. Also, it's very important that the THW is following an ASTM standard for a comparison with our techniques. A few things about the transient hot wire theory. According to this technique, the thermoconductivity of the fluid is calculated when we record the temperature rise of a thin metallic wire when this is immersed inside a fluid and when we apply to that a step voltage. So in that case, the wire is acting as a heating source that transfers heat from the wire to the fluid, and at the same time as a resistance thermometer from which we can calculate the temperature rise of the fluid. From the Fourier's equation of conduction, we can calculate the temperature rise of the fluid, of the wire and of the fluid, and from the slope of the straight line, we can calculate the thermoconductivity of the fluid. In this slide, you can see our THWL1 device. This device is suitable for fluids and pastes. For the thermoconductivity range is from 0.01 to 2 watts per meter per Kelvin. And additionally, with the THW software, it calculates the thermodiffusivity and the specific heat of the fluid. There is a wide viscosity range for the fluids, and the measuring time is only 1 second. The repeatability of the measurements is better than 1%, and the accuracy is better than 5% through the whole thermoconductivity range. And the temperature range for the basic model is from 10 to 200 degrees, and it can be from minus 35 to minus 50 depending from different models. It's also, there is an option to apply pressure of 20 bar to the fluid, and the smallest volume, it can be around 20 milliliters. As I said before, it follows the ASTM standard D7896. And because the THWL1 has a proprietary integrating heating and cooling system, allows uniform temperature during through the whole temperature range, which means that there is no natural convection effects and no disturbance during the measurements. In the THWL1, the user can easily pour the fluid inside the measuring cell, then can put the THWL1 sensor inside the cell, and because the short measuring time and the small sample volume, there is only small or no convection effects during the measurements, but if there is any convection effects, as I said earlier, it's very easy from the user to notice it. And as I said, the measuring cell, we can apply up to 20 bar pressure to the cell for measurements above the boiling point of the fluid. For measurements with temperature, the user can insert the measuring cell with a sensor inside the integrated temperature platform, and the THW software can automatically control these isothermal steps from 10 to 200 degrees or up to minus 50 degrees if it needed. Also, the Smart THWL1 software shows to the user if the quality of the measurements, if they are good or not, and give some notes. And the user can have a report of his results. He can save the result or export them to Excel file. Also, there is an option for the user to get an email with his results to his email address. This is the first page of the THW software. As you can see, the software detects the device and the temperature device on the THWL1. The user can change the sample name and has the option either to select the power for the measurement or press the detect power option. In that case, the device runs a thermal conductivity measurement, and according to that measurement can predict and calculate a specific, a suitable power for the measured fluid. After the user saves the results, has the option to go to run further measurements, and the case selects to have a schedule of measurements. As you can see, automatically the auto schedule has an option of the detect power at its temperature step. Also, the user has the option to change some measurements parameters, like the number of the measurements at each temperature step and the delay time between the steps. Here is an example of ethylene glycol results. As you can see, there is the power of the measurement and the quality of the results is good, which means that there are no problems with the measurement. And below its measurement, there is a graph of the temperature rise as a function of time. And also the user, with a right click on the graph, can move between graphs and also can get the temperature rise as a function of the logarithm of time, and a percentage deviations graph that actually is representative of the quality of the measurements. So what is the good or okay or poor notes that the user can see in the quality of the results? The good, as I said, means that all the conditions are satisfied, the measurement is good, the power applied is good, the temperature rise is between 2 and 4 degrees, and there is no disturbance in the measurement. The okay is usually that possibly the power during the measurements is high, and maybe the user manually can change the power. And poor means that there is a problem in the measurement. Either the user should increase or decrease the applied power, or there is a disturbance in the measurement. Sometimes it's like electrical noise or something like that. In the cases that the users are measuring very conductive fluids like nanofluids, they can see a poor quality measurements, but if the temperature rise is correct and follows the same trend like the previous measurements, then can ignore this method. It means that this fluid is conductive and there is a disturbance, but doesn't affect the thermal conductivity results. In this slide, you can see the thermal conductivity results of a fresh oil of 5W30 and the used one. As you can see in the picture on the left side, the first one is the fresh sample as we insert it inside, as we put it inside the measuring cell. And in the middle is the same exactly fluid after a run from 5 to 200 degrees. The third and really black fluid is the same oil when we get it from an engine, a car engine after 6,000 kilometers. And as you can see, there is a small decrease in the measured thermal conductivity of the used oil, and there is a disturbance in the high temperature results because no back pressure was applied to the fluid. So it was open, and probably because of the open cell, it was present slightly some natural convection during the measurements. In the next slide, you can see the thermodiffusivity and volumetric specific heat from the same two samples. And as you can see, and also in these two properties, the fresh sample had higher values than the used fluid. For comparison reasons, I will show you some results of water measurements and later of ethylene glycol. As you can see here, we have measured ionized water measurements and the comparison of the reference values, and the deviations between the measured values and the reference values is 2% for the case of the thermal conductivity, and around 3 or 4% in the thermal diffusivity and volumetric specific heat results between the measure and the reference values for the water. In the case of the ethylene glycol, there is a deviation of 1% between the thermal conductivity, thermal diffusivity, and volumetric specific heat through the whole temperature range between the measured and the reference values for the same fluid. And all these results, as I said, they are coming directly from the THW software. So the user is able directly to analyze and compare the results. We have different models of the THW. We have the portable device, the THWL2, that allows ambient pressure measurements. Depending on the accessories, there is a temperature range from -50 to 100 degrees. The repeatability is better than 2%, the accuracy is better than 5%, and there is a small volume of 15 ml. Also it follows the same ASTM standard. For the THWL1 device, this device is suitable for liquids, paste, and powders. The thermal conductivity range is from 0.01 to 2 watts per meter per Kelvin. It also calculates the thermal diffusivity and the volumetric specific heat. The repeatability is better than 1% and the accuracy 5%. There are different models according to the temperature range. The basic model goes from 10 to 200 degrees. Depending on the lab temperature, can start measurements from 5 or 0 degrees, but for longer waiting times. And we have also the THWL1S and THWL1E for temperatures from -50 to 200 or 300 degrees. And in all these three models, we can apply pressures up to 35 bar. Also, with these devices, we have different testing cells. We have the observation cell, where there is a Pyrex tube where the user can see any changes of the color or the composition of the fluid during the measurements. We have a powder cell for measurements of powders. We have a variable density powder cell where the user can change the density of the fluid through the thread that there is on the bottom of the cell. And we have the paste and PCM cell with the spring-loaded bottom cell, depending on the applications, the uses that everyone needs. Also, I would like to remind you for the upcoming webinars, you will get notifications for the next ones, and you are always welcome to saw them and hear them online from me and my colleagues. Thank you very much, and if you have any questions, I would be happy to answer them. We have a question. It says, what's the PCM sample? Is phase change materials, materials that can change with the temperature, can go from the liquid to solid phase, and we can, I had a previous webinar on measurements of phase change materials. If you would like, we can share them with you or you can find them in our website. And you can see the thermoconductivity results and the anomalous thermoconductivity change of these materials. There is a question if all the data that I show, it's an open cell setup. The cell is closed, but is open. I mean that there is no back pressure except of the water and the ethylene glycol results, where there I apply back pressure. But for the oil result, for the oil measurements, I didn't apply any back pressure during my measurements. But no, for the water and the ethylene glycol measurements, because even I went at higher temperatures, I apply back pressure. There is a question says, if the back pressure was applied in case of ethylene glycol and water, what would be the reason for a variation from standard results at high temperatures still? Let me go in the results of, in the case of water, there are no variations at high temperature. You cannot see any disturbance, because if we go in the measurements, for example here, you can see that with the temperatures the results are going up and down, but in the case of water or excuse me, or in the case of ethylene glycol, there are some experimental issues, but we are talking about 1% and 2% deviations. It's and the accuracy of the device is only, it's 5%. It's much better than the variations, than the deviations of the results at these temperatures. If you mean the variations of the results on the thermal diffusivity and specific heat, I want to say here that the THW is a technique for measurement, for thermal conductivity measurements. The thermal diffusivity and then the calculated volumetric specific heat are secondary properties measured. So, of course, in that case, we will have variations. Can we use this apparatus to measure thermophysical properties of ceramic sintered sample? If this is, I'm not sure if it's solid. No, it's not suitable for solid measurements. If it's powder, yes, it could possibly use it with a powder cell. But to tell you the truth, if I don't know the sample, if you don't explain me even later, if you have any questions, you can drop us an email and can answer you. If it's the sample, if it's like powder, we can measure it, and you can even change the density with a variable density cell. But if it's ceramic, no, you cannot. Do you think this could be used as an in situ lubricant condition monitoring method, say as a function of temperature, as a function of the it could, yes. The device can be in a lab. If you mean in line, no, but the device can be in the lab and measure the differences of the different samples of the oil while they're produced, or during, if you want to see what's the change of the thermoconductivity with the temperature. For the cost, you need to send an email to the info at thermtest.com and ask the salespeople about that. Of course, if you have any more questions, you can also, in the same email address, you can send an email for your extra questions, and I will be glad to discuss with you about your samples and your applications in more detail. Here I would like to thank you for being present in our webinar, and hope to see you again in the next one.